is we have to start 2D, okay? But the mesh will looks like that. If we say two-dimensional flow field, this line should be symmetry line, okay? Okay? Symmetry line. And we know from the lecture and from the exercise, to have a flow field, we need pressure distribution to point 1 and point 2, for example. Point 1 we will have vessel condition. That means you have to put in all the values for total pressure, total temperature, and if we say we have vessel condition, the velocity should be approximately 0. But Stars Lyceum don't like numbers like 0, okay? You have to put in the Mach number 0.002, okay? And the boundary for inlet is not velocity inlet. Please choose free stream. With okay, I will start the simulation here. Okay, so free stream inlet, and for number 2, this is pressure outlet, and for pressure outlet we need stagnation, the static conditions, static pressure, static temperature. That means static focus. Okay? Okay. The project, I will not give you, for example, the vessel condition, okay? I will give you only, for example, the Reynolds number. I will say you please investigate a Reynolds number, for example, 140,000, okay, with a nozzle diameter of D equal to 10 millimeter. If I say D 10 millimeter, this distance is radius, okay, this should be done in that, for that case 5 millimeter, okay. But please never forget to change this line to symmetry. If you don't change this to symmetry line, okay, you will have a half a nozzle and all your results will be done wrong, okay. That means please not forget to change the ball to the symmetry line. Okay, what I will give you is the Reynolds number, and in the lecture we have a definition for the Reynolds number and for the mass flow rate. The mass flow rate divided by throat diameter was a function of PO over square root of R times TO times square root of kappa times the stream function psi, and psi was a function of again kappa, okay? You can find that in the lecture notes from professor. And the Reynolds number based on the throat diameter is given by 4 times M. I don't know exactly now, okay, but I think that was something pi times D and another things, but I will give you the full description of the Reynolds number, okay? That means with given Reynolds number, okay, and given throat diameter, I will give you also the temperature you have to solve the inlet pressure. Okay? And if you have the inlet pressure, you can put the value for vessel condition. PO should be solved. Okay? TO I will give you, and the Mach number is 0.02. That means all the variables for subsonic inlet is given. Okay? And that means we can start a simulation after we define the outlet conditions. And for outlet condition, this is your task. You have to solve, you know, we talked about, if you remember this diagram, that was your pressure ratio, okay, versus X. With X, I mean, we have the nozzle, okay, pressure distribution along the axis in that case, okay. So that means we have a critical condition, PO asterisk 0.528, and the largest PPO is 1. Okay, this here should be then throughout this point. We have to reach the Mach number 1, okay? And after that, if you remember, we can have the first critical point. The first critical point was subsonic outlet, okay? Second critical point is supersonic outlet, okay? And the third critical point was if we have a shock exact at the exit, okay? Okay? That means firstly you have to solve all the variables for first, second and third critical point, yeah? And put into the STAR CCM simulation. So, this is your task. And the last part would be then what happens if we have shock here in divergent path, okay? That means you have here 1, 2, 3, 4 points for nozzle. Yeah? From Reynolds number, you have to solve the inlet pressure. With inlet pressure and geometry conditions, you have to solve the first critical point, second, third critical point, and what happens if you have a shock in the diffusor part. Okay? So, what we need is, what you have to plot along the axis. I need plots which looks like that. Okay? Plot for PO along symmetry line. Okay, I will show you how you can generate a plot along a symmetry line, and you have to compare all the variables that you solved analytically with the results from STAR CCM. That would be your first project. Okay, and we have 4 different groups. That means I will give also 4 different nozzles. For these 4 different nozzles, I will give also a lot of different Reynolds numbers. Okay, and please, we will help. We want to help you. Okay, don't copy your project. Yeah, please don't do that. Yeah, I don't like to say your project was a copied project from another student, and because of that you failed. Please don't do that. If you have a problem, write me an email or ask professor or me or my colleague. If you have time, we will help you. You know that. Yeah? But please don't copy. Yeah? I don't like it. So, okay, this is your first project now. How you can deal with that project? I will give you the mesh. You can download it next week. And that would be a nozzle, for example, like that. Okay. You see we have here inlet. Okay. This inlet should be free stream inlet, and we have pressure outlet. We have here 2D nozzle. Firstly, you have to go, if you say file, import volume mesh, and put in your mesh, the first thing what you have to do is go to mesh, scale mesh. Okay? First step, scaling mesh. Yeah? If you don't scale your mesh, the nozzle have a throat diameter